So, welcome to our eighth lesson in our study of mathematical biology 2. And here we'll be talking about conservative system. So, I'm Bodo Kanrinov, a final year student of mathematics, K University, and I'll be taking you through this lesson. So, let's take some definition. In mathematics, a conservative system is a dynamical system which stands in contrast to a dissipative system. So, roughly speaking, such systems have no friction or other mechanism to dissipate the dynamics, and thus their phase space does not shrink over time. Okay, right. So mathematically, when we say a system is conservative, right, it means that when you have a system of ODEs, like if you're going to consider a system of ODEs, it's said to be conservative if we have a function g of ui such that the following holds, right? Such that this equation holds. So if this holds, then we say that that system of ODEs is a conservative system, right? So that system is a conservative system. And we are going to, give you an example to explain to you what we are talking about, okay? So let's take an example here. It says consider the non-dimensionalized Lotka-Volterra predator prey model, right? So this is the non-dimensionalized one. So we have to determine whether or not the above system of ODEs is conservative. Alright, so as we said, a system of ODEs is conservative if there is a function g such that del g del ui is equal to summation I starting from 1 to m del g del ui times f I of ui is equal to 0. So if this condition holds, then that system of ODEs is said to be conservative. Alright. So these were the two equations we were given. Equation 1 and equation 2. Right. And we said that there has to be a particular function g. So that particular function g happens to be the solution we get for the two system when we do phase plane analysis, okay, in this case. So we have to find for that g, right? So to get that g, we have to perform phase plane analysis on the two equations you have in a system, right? So do that, we are going to see equation 1 divided by equation 2. That means we will get what you can see here. So when we simplify further, we will get the u div will be equal to, when we factorize u out here and a v out here, we get u multiplying 1 minus v and a v multiplying u minus 1. I hope you know the reason we don't have any detail here, like they will cancel out. Alright, so we can separate these into what variables using separation of variables, right? So when you do that, then you are going to get what you can see here, a multiplying u minus 1 over u du and 1 minus v over v dv, right, at the right hand side. Then you can see that our function is separable, right? The equation is separable, so we can solve them using the method of separation of variables, right? And so we integrate both sides, right? The left hand side with respect to u and the left side with respect to u and the right side with respect to v, right? So we just expanded what we had here. U minus 1 over u is the same as u over u minus 1 over u which is 1 minus 1 over u. So then we have our a, and the same thing applies here. So when we integrate, we have a constant here, 1, which is equal to u, we get u. So here we get a u of tau. The u of tau means that u is just a function of tau. Then this will give us, when you integrate 1 over u, you get ln u. But u is a function of what, tau. That's why we have it here. So minus a ln u of tau. Then it will be equal to ln v of tau. Then it will be minus v of tau plus an arbitrary constant c. So when you make the c the subject, we have this. Now we are saying that let our function g of uv be the c, which is equal to this, right? So that is the function g that we're supposed to find. I hope you get it, right? So after finding for our function g, g is a function of what, u and v. So we would have to differentiate g partially with respect to u and also partially with respect to v. So del J del U will give us a minus a over u, right? When you differentiate this partially with respect to u. When you also differentiate this partially with respect to v, you're going to get 1 minus 1 over v. Okay, alright. But for this system to be conservative, right? It means that summation I starting from 1 to m del J del ui times f of I ui, which is equal to, in our case, del J del u times f1 of uv plus del J del v times f2 uv should be equal to what? 0. So we have found del J del u and del J del v. So we have to look for f of 1 f1 uv and f2 uv, right? So this is f1 uv and this is f2 uv. So this is how we get it. We get them from the right hand side of the equations we had, right? So these are f of 1 uv and these are f of 2 uv. So I hope you get that. Alright, so if you get that, then let's do substitution. So when you do substitution, then we are going to get a minus a over u multiplying u minus uv, then plus 1 minus 1 over v multiplying a uv minus av. Alright, we just made substitution. So when you expand this, you get au minus a minus auv plus av. When you expand it, you get plus auv minus av minus au plus a. So au minus au minus a plus a minus av plus auv, this. Then like we get what, 0. So since the sum is 0, then it means that the system is what, conservative, right? So when you have a system of ODEs, that's how you show whether it is conservative or not, right? So if it had not been 0, that means the system would have been non-conservative. Okay, so thank you very much and see you in lesson 9. And in lesson 9 we'll talk about the diffusion equation and how to derive that. Okay, because we are going to use that in our models. Okay, all right, so thank you very much and see you in the next video.